Hello again. So today I'm going to be telling you about integrals. So there's two types of integrals. There's indefinite integrals. And so these are usually written like this. The integral of f of t dt is how we write that. And this is new notation, but it's actually an old concept. These are the same thing as antiderivatives, and we've done plenty of those so far this course. So the answer to these includes an arbitrary constant, and we are still going to be using them. But I just wanted to draw your attention to the fact that there's two different kinds of integrals. And the other kind of integrals is called definite integrals. So a definite integral is an integral which is written like this. So the contrast here is that there's nothing here. There's no numbers here in an indefinite integral. And that's what makes it an indefinite integral as far as notation is concerned. There's numbers here. Usually it'll be like 1 and 2 or 5 and 6. In this case, I've written arbitrary numbers A and B. And so there's numbers here, and that's how you can tell that it's a definite integral. So definite integrals are new. We haven't defined them before. We haven't seen them before. The answer is a number. There's no arbitrary constant in a definite integral. And we're going to use something called the FTC to compute these. And the FTC stands for Fundamental Theorem of Calculus. So we'll cover that in a little bit. But before we do that, I'd just like to go over a quick example of both types of integrals. Now, I don't expect you to be able to compute these on your own yet. You probably have no idea how. But I just want to give you a feel for what these computations are eventually going to look like. So this indefinite integral here is asking us to compute an antiderivative of x cubed. What is an antiderivative of x cubed? Well, x to the fourth over 4 is 1. So is x to the fourth over 4 plus 7. And in general, the most general antiderivative for this is x to the fourth over 4 plus c. So that's our answer, x to the fourth over 4 plus. So actually what this is asking us to compute is not just any antiderivative, but the most general antiderivative. And that's why our answer is always going to include that extra constant c. In contrast, this definite integral here is asking us for a number. The answer to this problem is ultimately going to be a number. And the computation for one of these looks like the following thing. First we find an antiderivative, and then we evaluate that antiderivative at two different points. So that's what this vertical bar means. It means we're evaluating it at the points that we write above and below. And we're going to evaluate at the top point and then evaluate at the bottom point, and we're going to subtract off the bottom one from the top one. So that looks like the following: 3 to the fourth over 4, because we have x to the fourth, and we're just plugging in 2 for x, minus 1 to the fourth over 4. And so our final answer for this would be 15 over 4. So the answer to this is a number. The answer to this is a function and an arbitrary constant. But these things are related, because this thing is what we put in here to compute the definite integral. And actually, it would have been fine if we put in that arbitrary constant as well. If we had done that, what we would get would look like this, and then this plus c and this plus c cancel each other out, because this one gets a minus sign. So since these two c's cancel each other out, usually we don't write the c at all for a problem like this, and we just leave it out. But just FYI, any antiderivative would work, even the most general one, which includes the constant c. It's just that would be extra trouble to compute, so usually we don't use it. But now let's back up a little bit and go over some terminology, and then we'll sort of go over how we're actually going to compute definite integrals in detail. So first of all, I need to introduce to you some terms. And some of these apply to both indefinite integrals and definite integrals, but some of them only apply to definite integrals. So we've got 3 integrals here, and I'll just remind you. The first integral is indefinite, and the other 2 are definite integrals. And now I'm going to break these integrals apart into their constituent parts, and I'm going to tell you what each part is called. So the first thing that we need to cover is called the differential. So the differential is the little letters at the end of each integral. So it's this dt, dx, and dy. Those are the differentials of these 3 integrals. The second thing that we need to cover is called the integral. The integral is the whole thing, so it's not really a part of these at all. The third term we need to cover is the integrand. You can kind of think of the integrand as the thing you're integrating, or the thing being integrated, or the thing that you're taking the integral of. The fourth part of these integrals that I want you to know the word for is the integration symbol. That's just this big long S here. The last thing that I want you to know is this term called the bounds of integration. So this only applies to definite integrals, and it's these numbers here. So sometimes the bounds of integration are called limits of integration. So that's not actually technically a correct term, so I'm going to try to call these bounds as much as possible, so that's what you'll generally hear me say. But just so you know, sometimes when people are speaking informally, they do call these the limits of integration. Alright, so let's actually compute some integral. So there's a lot of rules for working with integrals, but most of them are pretty simple once you get used to them. The first thing is that you can switch the bounds of integration by putting a minus sign in front of your whole integral. So if you switch the bounds of integration in any integral, it makes the whole thing negative. So an example where that happens is the integral from 1 to 0 of cosine of t dt equals the negative integral of 0 to 1 cosine of t dt. So that's a little bit odd. We usually don't actually get integrals in this form unless it's in the middle of a problem. So we're not going to see a whole lot of this right now, but when we get to some more advanced integrals later, especially when we cover the method of substitution, this type of thing will come up occasionally, and usually when we get bounds that are out of order like this, where our lower bound is actually bigger than our upper bound, the first thing that we want to do is switch those two so that we get a normal looking integral. The second good rule for dealing with integrals is when you've got three numbers, a, b, and c, that are in order, and you've got an integral from a to c, you can actually split that up into two different integrals, one from a to b and the other one from b to c. And the same thing works in reverse. If you have an integral from a to b and you're adding it to an integral from b to c, you could combine that into just one integral and save yourself a little bit of work. So here's an example where we might want to do that. This is the integral from minus 1 to 1 of sine of theta d theta, and we can actually split that up, picking 0 as our point, which is in between minus 1 and 1. We can split that up into the integral from minus 1 to 0 of sine of theta d theta, plus the integral from 0 to 1 of sine of theta d theta. And the reason why we might actually want to do that is that this integral is going to turn out to be some constant. This integral is going to turn out to be the negative of that constant. So this integral here, the whole integral on our left, is actually going to turn out to be 0. So there are actually examples where we would want to do this type of thing, although it might not be immediately obvious now. The third rule for computing integrals that I want you to know is called linearity. Linearity tells us that if we've got a constant times one function plus another constant times another function, and that's our integrand, what we can do is we can actually split up the integral. We can pull out the constants, and we can also turn this one integral into two integrals. So here's an example where you might want to do something like that. The integral from 1 to 10 of e to the x plus x squared dx is actually the integral from 1 to 10 of e to the x dx plus the integral from 1 to the 10 of x squared dx. The reason you might want to do something like that is because then you can kind of handle this term and this term separately. So if you're able to find an antiderivative for this thing pretty easily, but it's really hard for you to find an antiderivative of this thing, then you can handle this thing separately and just write the answer off to the side while you work on this thing in more detail, instead of carrying this baggage with you for the entire computation. Another example using this property of linearity is if I have the integral from 1 to 10 of 5 e to the x dx, I can actually pull out the 5. And you might be wondering, how did I get this type of trick from linearity? Well, really what I've done is I've just set d equal to 0 here, and then there is no second term. So this is actually a consequence of our linearity property. But the important thing to realize here is, just like when taking derivatives, when you're computing integrals, you can pull out a constant. Finally, there's one more big rule of integration that you've got to know, and this is the fundamental theorem of calculus. Usually, because that's kind of a mouthful, we say FTC for short. And there's actually a second half of the FTC, an FTC part 2. We're going to cover that in a future lesson. But most of the time when people talk about the FTC, or the fundamental theorem of calculus, what they mean is this theorem right here, which says that if you have two functions, g and f, where g prime of x is equal to f of x, then the integral from a to b of f of x dx is g of b minus g of a. So what that informally says is, if g is any antiderivative of f of x, then the integral from a to b of f of x dx is the difference in g evaluated at the two endpoints. So g of b minus g of a. So let me give you an example where we apply the fundamental theorem of calculus. This is probably going to be the most common technique used to compute integrals for the rest of this course. So if the problem asks us to compute the integral from 1 to 10 of x squared dx, I'm going to identify this function here as f of x. This is my integrand, right? So now I've written this as an integral from a to b of f of x dx. So in order to apply the fundamental theorem of calculus, I've got to find some function g of x such that g prime of x is f of x. In other words, I've got to find an antiderivative for f of x. In this case, my function f of x is pretty simple. It's just x squared. So the function g of x equals x cubed over 3 will work. There's other possible functions we could choose, like x cubed over 3 plus 1, or x cubed over 3 plus an arbitrary constant. But we're just going to go with x cubed over 3. The reason we're going to pick this is because it's the simplest one, actually, and that's going to make our computation the easiest. And generally, when you're computing an antiderivative, you should probably check that it's correct. So I'm going to go ahead and compute the derivative of this g here, and that turns out to be 1/3 of the derivative of x cubed, which is 1/3 times 3x squared, which is equal to x squared, which indeed is the f of x that we started with. So this antiderivative is good. This is going to work. So now that we've got our antiderivative, we need to apply the fundamental theorem of calculus to solving the problem. So it's pretty simple. All we do is use this formula. In this problem, a is equal to 1 and b is equal to 10, so g of b minus g of a turns into g of 10 minus g of 1. Computing that, we find out that g of 10 is 10 to the 3 over 3, and g of 1 is 1 to the 3rd power over 3, which is equal to 333. So that's our final answer. Incidentally, sometimes we write this with a different notation. So sometimes we would write this difference, g of 10 minus g of 1, as g of x evaluated at 10 and 1. And it's totally fine to write either of these, whichever one you prefer. So now I'd like to tell you a little bit about what these terms mean conceptually. So the lesson here is that definite integrals are equal to the exact change undergone by a function, which is equal to the area under the curve of the derivative of the function. So the definite integral of a function's derivative is equal to the exact change in the function, which is equal to the area under the function's derivative curve. So previously we had this problem. We were asked to compute the exact change in the function with derivative f prime of x equal to 1 plus x over 2 between x equals 1 and x equals 2. And we were actually able to compute this problem algebraically, and it turned out the answer was 7 over 4. So now we're going to solve the same problem using an integral. So in this case, we want to find the area under the curve 1 plus x over 2 between x equals 1 and x equals 2. So my bounds of integration are going to be x equals 1 and x equals 2. And my integrand is going to be 1 plus x over 2. That's the thing I'm integrating. So the first thing to do here is to find an antiderivative for 1 plus x over 2. So one antiderivative that'll work is x plus x squared over 4. And we can check that. If we take the derivative of that, what we find is that we get 1 plus 2x over 4, which is equal to 1 plus x over 2, and that's the function we started with, so we're good. So this is our antiderivative. So what that tells me is that this integral is the antiderivative that we just found, x plus x squared over 4, evaluated at the two bounds of integration. So if we plug these numbers into this formula, the answer we find is 7 over 4. And just checking, that actually agrees with what we found previously. So both of these techniques give us the same answer. So here's another problem that we did before. We wanted to find the total change in the function f of x equals x minus 1/4 x squared on the interval from x equals 0 to x equals 3. So geometrically, we drew a picture like this, and we found out that the answer was 3 over 4. So now I'm going to solve the same problem using an integral. So our function is f of x equals x minus 1 over 4 x squared. So the thing we want to integrate here is actually f prime of x. And we want to integrate that function between 0 and 3. So computing f prime of x is pretty easy. It's just 1 plus x over 2. So we're computing the integral from 0 to 3 of 1 plus x over 2 dx. Now, the problem actually gave us an antiderivative for our integrand already. So applying the FTC is easy, and we just plug in the values from the bounds of integration to find that the exact change is 3 over 4. And I'll just point out that, of course, that agrees with what we found previously. So finally, I'd like to show you a more complicated example. So this example tells us that the vertical component of the velocity of a projectile is given by h prime of t equals 4t cubed plus 2t. And t is time in seconds, and We're given also that the height in meters at time t equals 0 is h of 0 equals 5. And the problem asks us to find h of 2, i.e. the height at time t equals 2 seconds. So, by the fundamental theorem of calculus, the integral from 0 to 2 of h prime of t dt is equal to h of 2 minus h of 0. So I'm actually just going to rearrange this until we get what we want. What we want to find here is h of 2. The problem gives us this h of 0. And this here is something that we can compute, this integral. So I'm just going to rearrange these terms so that I've solved this equation for h of 2. So I've rearranged this equation, and it shows me that h of 2 is equal to h of 0 plus the integral from 0 to 2 of h prime of t dt. And the problem actually tells me that h prime is 4t cubed plus 2t. So that's great. I can just plug that straight into my integral. And it also tells me that h of 0 is 5, so I can plug that straight into my equation as well. So I need to find an antiderivative of h prime of t equals 4t cubed plus 2t in order to apply the fundamental theorem of calculus and compute this integral. By applying the reverse power rule to both of these terms, 4t cubed and 2t, I'm able to find that a potential antiderivative is t to the fourth plus t squared. And actually, I can add any constant to that I'd like. But for purposes of the FTC, actually, I can use any antiderivative. So I can pick this constant to be whatever I want, so I'm going to choose that to be 0. And that is just going to get rid of that term and simplify my computation. So now I can use this antiderivative for this integrand to continue my computation. And what I find is that the integral from 0 to 2, 4t cubed plus 2t, is equal to t to the fourth plus t squared, evaluated at 2 and then evaluated at 0. So carrying this 5 along, what we find is that our answer is 2 to the fourth plus 2 squared minus 0 to the fourth minus 0 squared. Obviously, the second term drops out, and we're left with 5 plus 16 plus 4, which is 25. So it turns out, just summarizing, that h of 2 was equal to 25 meters. And one thing I want to point out about this problem is this derivative is really weird. It's got a cube in it. That's really not how most projectiles or rocket ships or other common velocities behave. So even though we're not really able to apply any sort of physical intuition to this problem, calculus still gave the answer just fine. All right, that's all for today, so have a nice day.